My name is Ben Follett, and I am the U.S. Product and Marketing Manager for SCIA Inc. And today I want to talk a little bit about our product, SCIA Engineer, but more specifically, how having CAD-like modeling features and structural analysis in the same package leads to more streamlined designs for industrial structures. And so a little bit of background to start. For those of you who aren't familiar with SCIA Engineer as a company, or SCIA, excuse me, as a company, we are actually owned by the Nemecheck Group. The Nemecheck Group is a global AEC software company that operates all over the world in all different types of regions. We're headquartered in Munich, Germany, and SCIA, the software company, is headquartered in Herkestad, Belgium, just outside of Brussels. Like I mentioned, that we work specifically in the AEC group or AEC space, in the sense that we own Nemecheck owns software packages throughout that design space. We've been around for 50 years. We have over 1.8 million users in 142 countries and 1,700 employees worldwide. And you might not know us by the Nemecheck Group, but you may know us by our brands. And so these are currently the brands of the Nemecheck Group. We have brands like Allplan, Graphisoft, and Vectorworks, which are all kind of modeling, architectural, CAD-like packages. Graphisoft, their package ArchiCAD, and Vectorworks both being very popular architectural softwares here in the United States. Also, recently we've grown by acquisition. In the last couple years, we've acquired Bluebeam. Obviously, many engineers know Bluebeam from their software to create and modify and update PDFs. And then also more recently, SDS2 Design Data, the package for steel building fabrication, design or modeling, erection, detailing, and also connection design. Today, though, the package that we're going to focus on is SCIA Engineer. And SCIA is the finite element analysis, structural analysis, and design package within the Nemecheck Group. And so before we jump into kind of a little bit more information about SCIA Engineer, everybody always asks, who uses SCIA, worldwide, who uses SCIA in the States. And so just kind of a group of customers. These are more, in some cases, either larger companies or in some cases industrial companies that use our software both here and abroad. And so you can see we have a lot of large companies that are using SCIA for a wide range of projects. And that wide range of projects really consists of office and residential complexes, industrial structures, which is where we're going to kind of focus today, energy-related structures like towers or masts, infrastructure projects, environmental structures like tanks or pools, and then also specialty structures. All of these are structures that can be designed and are designed in SCIA Engineer. And so before we jump into some live demonstration of the software, really when we talk about SCIA Engineer, whether it's for commercial buildings or it's for industrial structures, we talk about SCIA in these four key benefits. And our four key benefits are fast and efficient modeling, the advanced analysis and multi-material design in one package, automatic and coordinated documentation through what we call the engineering report, and then interoperability and post-processing. This is obviously interoperability with BIM, with BIM through Revit or Tekla or IFC. So we're going to focus today mainly on the first two benefits, the fast and efficient modeling and the advanced analysis and multi-material design. We just ran a webinar last month about the engineering report, automatic and coordinated documentation. You can find that on our YouTube channel. Just search SCIA or SCIA Engineer. And then a few months prior to that, we did a big webinar about Revit if you're interested in that. Oops. So let's go ahead and jump into some live demonstration. And so here I just have kind of a really a hopper industrial-like structure. This is actually a real project that we worked on with a company, and so I want to use this to kind of demonstrate start by demonstrating some of the advanced 3D modeling capabilities. And so in many cases you're starting with geometry from scratch, but also in many cases you're starting with geometry that you're receiving from some outside source, whether it's from an architect or mainly in these industrial-like structures. Maybe you're getting equipment cut sheets, or you're getting drawings of equipment. Maybe this hopper or this tank has a size and a sheet in an AutoCAD drawing or something like that. And so in many cases we can import geometry, whether it's importing through use of the table input or which opened up on my second screen. We could just drop in coordinates in the table input. We can also use the import of DWG, DXF, and VRML, so these kind of vector-based image file formats. We can import those directly. We also always have the ability to import directly XML files, Revit files, Tekla files, or IFC files. So all of these different file types are a possibility when you start. And really, the idea here is to be able to leverage the functionality or leverage the work that's already been done by someone else so that you can be more efficient in the structure that you need to create. Additionally, we have a really robust cross-sectional library. So in this particular case, this is just a cross-sectional library that exists in this project, and then if I click New, we have this entire cross-section library that we can add from. We can choose a filter, to filter based on the type of project that we're looking for or where the project's located. So we don't just have standard profiles or profile libraries, but also more complex paired shape, closed shapes, haunches, welded shapes, sheet welded shapes, thin wall geometrics, so cold form or aluminum shapes. So really anything that you want in this very robust profile library, whether it's steel, concrete, thin walled, etc. One of the real advantages of SCIA, though, in terms of profiles or cross-sections, is the ability to create what we call a general cross-section. And so we have what we call the general cross-section editor. This comes in SCIA Engineer, and really the option or the availability here is to create your own cross-section. So whether it's just by modeling polygons or it's by modeling thin-walled shapes, whether it's by combining sections from a library, maybe it's a tube with a WT welded onto it or something like that, or it's by importing a cut sheet of a particular cross-section from a DWG file. All of these things can be leveraged and used to build custom cross-sections. Once we use those, once we build those custom cross-sections, we can actually use that to create, in this particular case, I've created this custom cross-section. This isn't a standard shape that exists in SCIA, but it is one that we can utilize. And so we can also do multi-material, so we can see I've got materials different in the WT as I do in the channel. Now we can use this and run a 2D finite element analysis. So we can run that finite element analysis to generate all the properties of this particular shape. And by that, using those properties, we can use these properties when we do modeling, when we do analysis, and so on and so forth. So now this particular shape, this cross-section, is a cross-section that we could use both in modeling and in analysis, and even for most steel check, we could even use it in the steel check. So we can use all the properties to determine the steel check of this particular element. Okay. So when we start modeling, when we have cross-sections defined, when we start to model, we have the ability to model out of what we call the structure service. And so if I double-click on structure, we can see the different type of modeling capabilities that we have here in SCIA Engineer. And so these are just structural modeling capabilities. And so if we select any entity, so in this case, if I select the member modeling tool, this is a modeling tool that is just used for simple input. So we're going to input the I node and the J node on screen, just like you would if you were modeling in AutoCAD or Revit or another software. And so you can see all the properties that can be defined for this particular element. If you don't define a property correctly, you can always define that property later by selecting the element and then looking in the properties palette. And so this is really used for fast and efficient modification of element properties, as well as using results later. And so we'll see that later. And so what I'm going to do is I'm actually going to start with the column tool, and we're going to go ahead and start modeling in. We're going to just start modeling in some additional frames here. And so I'm going to start by picking just a cross section. So we'll choose a cross section. Maybe this 8x40 will work. We can set some other criteria. This cross section, maybe what layer it shows up on, what the length is. So in this case, it's a height of 11.5 feet. And then I'm going to go ahead and click OK to come into the input. Now you can see all the different snap points. The snaps are driven by this cursor snap settings. The cursor snap settings is essentially O snaps from AutoCAD. And so you can see we can enable all these different project snaps to be able to really quickly and easily snap to certain points in the model. And so with those snaps on, I'm going to go ahead and just start to drop certain things in at different locations along the geometry here. So I'm just going to go ahead and pick a few nodes here to create my structure. So we first have those columns. Now next, if I want to model in maybe some beams that connect these elements, I could use my member tool. Again, select a cross section. Maybe we'll select this, let's pick something smaller than that. So let's pick maybe this 12 by 22. You'll notice that there's no length established because we're going to establish this length on screen by just clicking the I and the J nodes. And so you can see down here in the command line that the first part of the command defining the start point is available. You can also see here the modeling tools. So right now I'm in the straight line modeling tool, and if I do that I can just click on our start point and our end point to start to begin to model in the structure, right? And so I can rotate around to be able to see my snap points, find my orthogonal points, and so I can really quickly build this geometry here. So let's just finish building. Snaps are jumping there. There we go. And then we'll finish up with these ones here. Now, one of the things you've noticed here is that we have these beams. Maybe they're not set to an alignment here, a proper alignment, and so we can change this member system line to be one of any number of different system line configurations, but really we want top of steel here. So I can just shift that to top, and we get all those members to be top of steel. Now we can do any number of what we call geometric manipulations. We could copy, move, multi-copy, rotate, scale, extend, trim, break, all of those things that you would find in AutoCAD or Revit in a CAD-like environment. You can find those again in SCIA Engineer. And so really the idea here is that you don't have to relearn how to model in your analysis software. You can utilize the same modeling techniques that you've learned and probably mastered in your drafting software. You can use those in a software like SCIA Engineer, so making the modeling really an efficient process. Now, one of the things while we're working in a model, especially a model of this size, one of the things that is beneficial is being able to use what we call activities. So activities are a way to organize. Let me just bring down the menu here so we can see it. Activities are a way to organize and filter the model. So they include activities by selection or activities by clipping box, activities by layer. SCIA, like AutoCAD, can have everything on different layers, and those layers can be turned on and off. And so one of the things that we want to be able to do is I'm going to go ahead and show how we can kind of use the activities to filter and then grab very specific things. So I'm going to choose a layer activity, and I'm going to select that I only want the chute. And this kind of big hopper is what I'm calling the chute here. So I'm just going to see the chute now. So with the chute active, what we can do is we can modify the overall dimensions of this chute. So for instance, if I go ahead and select this particular node here, I can use some of the selection tools to say, hey, I want to select all other nodes that have that similar property. So I'm going to select the property here, and I'm going to use what we call the Select Elements by Property tool. I affectionately call it the lightning bolt tool. And so if I do that, it's going to select all those other nodes that had that same x-coordinate. And so with that, we can go ahead and change that x-coordinate from 44.5 feet to maybe 45.5 feet. And so just shifting that out. Maybe we knew, or the manufacturer sent us an updated cut sheet, or we got updated information based on the opening size, and we need to make those changes from whoever. We can really quickly and easily make those changes. Now in addition, we can go ahead and maybe add in some additional stiffeners. So if I go ahead and choose the 2D member modeling tool now, I'm going to go ahead and use the plate tool. I can set a material and set a thickness, and we can just start modeling in our plate. And so let's go ahead and model in maybe along the back here. We can model in our plate. Now we can set our snaps or our dot grid so that our spacing is set to a certain amount. So if I wanted to come a half a foot out, I could set that and then use some of my snapping tools to very quickly and easily draw in that plate, right? Now I can take that plate and use the copy command and just go ahead and copy that plate down. And now we have kind of these stiffener plates that are all around the structure. So we have these plates. Now with these plates, we can also adjust the steel frame due to the chute changes. So we've changed the chute now. Obviously the steel frame has to change. So let's go ahead and turn off the activity so that we can see everything again. And now we can see that this, that our stiffeners and our chute interact now. They're too close to this. And so again, I can use that same tool. I'm going to select one node, and say, you know what, I want to adjust everything that's along this line. So if I go ahead and say I want to adjust everything on the x-coordinate 46, it's going to find all those coordinate positions for me. And then we can go ahead and say I'm going to remove these coordinates of the stiffener because we don't want to remove the stiffener. And then we can go ahead and shift these to, say, 47. So very quickly and easily there, we can see now that the frame is now changed. It's updated based on the fact that we made a quick change to the chute. And so we can just really quickly and easily and interactively make these changes to the structure when changes occur. Because we know as structural engineers that one of the biggest things that we encounter are changes, whether they're changes from the architect, they're changes based on, in this case, maybe the chute needing to be resized because of product requirement, the load requirements within it, whether it's, sand or gravel or whatever grain that's going through this particular chute. And so we've got that whole thing. Now in addition, we can go ahead and add in a steel plate on the floor. So again, we can maybe choose a certain thickness and just use, again, our snaps to just model in, the extents of a plate. So I'll just kind of drop a plate on this particular portion here. And so we could put a plate on that. That can be a deck. We could change that to a metal deck of some sort and then choose a Volcraft metal deck or something like that. It's completely up to you at that point, and it's really just a matter of how you want to model. Now, obviously there's many other robust features in SCIA Engineer based on modeling, whether it's 1D or 2D modeling. We have the ability to model with shells, whether they're shells are 3D elements, not planar elements, so whether they're more complex shells. But in this case, we also want to look at how to model kind of in a robust fashion when we're looking at loading. So in particular, we've got this very kind of interesting geometry for the chute here. And so because of that, we've got some probably interesting loading conditions. And so typically in SCIA Engineer, individual loads are added to an individual load case. And so we've got a group of load cases: permanent load, equipment and soil load, normal load or maintenance mill load, floor load, walkway load, the full chute. So whatever it is, we've got these different loads or load cases that we apply. So once we have a load case, we want to then apply a load to the particular structure. So again, let's look at applying the load to a specific type of load to the chute here. So I'm going to go ahead and turn back on this activity for the chute just to give us the chute. I'm going to go ahead and switch this to another layer so it's not part of it. Let's put this on the slab layer and it'll disappear. Okay. So the first thing I'm going to do is I'm going to go into the load service, and we can see all the different loads that we have: point loads, line loads, regular surface loads, thermal loads, moments, point displacements, line displacements, just a variety of different loads, all kind of your normal type of loads. Now, one of the types of loads in all point, line, and surface loads that is pretty unique to SCIA Engineers is what we call free loads. And so free loads are surface loads that can be drawn and then projected on any number of surfaces together at the same time. They don't have to be on an individual 2D member surface, and they can also be variable. And so the first thing I'm going to do, I'm going to draw in a load that's kind of on this sloping part of the chute here, right? But I also want it to be variable in this vertical direction here, or this. So the first thing I'm going to do is I'm going to shift my working plane. I'm going to set my UCS just like I would set my UCS if I was doing something in AutoCAD. I'm going to set it according to the entity LCS, meaning that I'm going to go ahead and I'm going to select that I want to pick. Let's go ahead and change my selection tool here. I'm going to pick that I want my working plane to be aligned with one of these panels or one of these shell elements or plate elements that's in the model. So in doing so, my drawing's just updating here. So in doing so, I'm going to go ahead and set that so that I can really work on that particular plate, or that particular plane. So I'm going to go ahead and select according to entity LCS. So this is going to select my working plane defined according to the local coordinate system of a particular element. And so when I do that, we can go ahead and select this plate. Now in selecting this plate, this is going to, like I said, give us the opportunity to draw in a surface load that is really in that particular direction. Okay, so I selected that, and we're going to set our working plane in that way. Okay, so now we can go ahead and draw in our surface load. So I'm going to choose that I want to do a free surface load. So I'm going to instead of choosing the regular surface load on a 2D member, I'm going to choose that we want to do a free surface load on the workspace. So I'm going to choose free surface load here, and we can set the value. So we're going to set the direction. Here you can see, since we set that working plane, this Y direction is vertical, and so we want that direction distribution to be that vertical direction. We can set our variability, so we can set our Q1 to be, I think we'll do like a -300 and a -100, and then we can set our geometry. Do we want it to be in the global system, the coordinate system of the particular member? And so with that all set, we can go ahead and we can kind of model in our geometry here. So I'm just going to use the snap points here and just kind of rotate around here to get us something that's pretty close to what we want. Okay. So now we've got this load, right? So we've got this load that's being applied on the structure. Now we can see that we've kind of got this reversal, so probably just need to change our values here. Let's see. Again, I think this is just a drawing thing here. So if we look at this, we've got probably what we want. And so now with this load, we can go ahead and utilize this load to create this variable load from this variable pressure on the structure. And so in doing that, we can create that load very specifically in the way that we want. And now this load is going to get generated on all the different panels. It's what we call a free force, a free surface force. It's going to get generated on all the panels and distribute to all the panels accordingly. And so those are a few of the advanced modeling types. So before we kind of go into looking at some of the analysis, let's just talk a little bit about some of the advanced analysis elements that exist in SCIA Engineer. So really we have extensive analysis. One of the really nice things about this is that all these analysis features exist in the same package. You're not buying additional softwares to do different things. There's not an additional software to do buildings as there is one to do industrial structures or something that's buildings or something that's a little bit more specialized. That's all done in SCIA Engineer. And so you can see, in addition to just your standard linear analysis, you have different types of nonlinear analysis, advanced nonlinears like cables or springs, friction supports, general dynamics, free vibration, harmonic, time history, do a seismic analysis, whether it's response spectrum. We have what we call the improved reduced system. You can do pushover. Obviously, you can do a simple equivalent lateral force procedure. And then something we'll talk a little bit more, but soil structure interaction and then stability analysis, both very important for industrial or tank-like structures. So one of the advanced analysis features, nonlinear, right? And so what are some example use cases? We see these obviously with brace frames when we're doing a tension-only element, doing guide mast when we're doing steeled cables or steel cable supported structures. Obviously something straightforward that we all know from the AISC, which is the direct analysis method. We have different types of calculation methods, and the software will choose them based on your structure, but you can always manipulate them. And then just some of the requirements. You always need nonlinear combinations, obviously. You need to set the right calculation method. And sometimes if you want to do something like the direct analysis method, you need those local or global imperfections. We can see a redistribution of applied loads from a nonlinear analysis. Obviously, we get better equilibrium sometimes of the structure based on the deformed shape. And then obviously we comply with the AISC steel code checks when we're doing something like the direct analysis method. Another advanced analysis is dynamic analysis. And so like I mentioned, we just can do a free vibration natural frequency calculation. We can get a resonance calculation, so we could take maybe a piece of equipment and we can add a mass to it and then vibrate that mass to understand how that piece of equipment is going to affect the vibration or the frequency of the structure. We can also do seismic or other more advanced dynamic analysis or even a harmonic load. And finally, the last one is what we call a stability analysis. So basically the idea here is that for more advanced or more complex structures, the kind of typical K factors, the typical buckled shape, that you would find or that you would know kind of just off the top of your head from AISC really doesn't apply to that type of structure. In this example, this is like a racking structure. And so really this stability gives you the opportunity to search for the real buckling mode that would lead to collapse or failure of the structure. And so you can see this can validate your model. You can get, using the Euler buckling theory, you basically use stability combinations as types of kind of eigenmodes and can determine then how the structure buckles. And so what you get is you get not only graphically the buckled shape of the structure, but also get the critical load coefficient, so kind of the multiplier of whatever load you've got applied to the structure at that point in that combination, at which that buckling will occur. And so you can find out very quickly if that's under 1, that structure's buckling under your regular load is a failure. And if it's obviously over 1 or some order of over 1, you can see how kind of safe and stable your structure is. And so you can see very easily on a large structure, where do I need to add bracing on plates, where do I need to add bracing? And so let's go ahead and jump back into SCIA Engineer. And I'm going to just switch files because I have a file that has some analysis that's already run, so we can go ahead and look at some analysis things in the software. And so with the analysis already run, I'm going to go ahead and go into the results service here. Now before we go ahead and look at the different types of results, the one thing that always comes up when we talk about plated structures, especially where we can see a plated structure like this particular chute, is meshing. And so again, I'm going to use that layer activity to show just the chute of this particular model. And so this is that chute, and these are plate elements, and all these plate elements are being meshed, right? And so what SCIA does, SCIA has meshing that is automatic. So the user will set a global mesh size and then can use either local refinements or automatic refinements based on the loading conditions to refine that mesh. So we can do local refinements at a node, at a panel, or a surface, or along the edge of a surface. Or the automatic mesh refinement allows you to say, hey, I want to refine the mesh, and for instance, if we had load on the interior of this, I want to refine the mesh based on the load that's applied to it. And in doing so, what SCIA will do is it'll actually take the load, it'll take the results from adjacent mesh nodes, it'll compare them to a tolerance that you've set, and it'll refine that, it'll propose a refined mesh that then fits that tolerance that you've set. And so that really takes all the guesswork out of doing refinement, and also really speeds up that process. Doesn't require you to refine and maybe have too coarse of a mesh or too fine of a mesh, and so it really does a really great job. And it's really advanced. It's written. It was created based on some papers that we wrote with the Technical University in Prague and some others, and I can share those papers with anybody that's interested. And so because we have an automatic analysis or an automatic mesh refinement, I can just go ahead and turn on the mesh. And so I'm just going to enable the visibility of this particular mesh. These, as you can see, are just kind of a denotation of those particular refinements. I'm going to go ahead and turn those off. And so we can see the mesh then that was generated on the structure. So this is the mesh. You can see that we have larger and smaller meshes based on those refinements. We can see the refinements in this plated portion, these support structures. And so we can see how this mesh is going to be used to give us our loading, or excuse me, give us our results. Now, one thing to mention is that you'll notice that this element here is broken up into 9 mesh elements, but it doesn't get subdivided. It doesn't physically get broken up. This plate is always this plate, right? It's always going to be this shape. It's always going to be this size unless you make a change to it. It doesn't get subdivided. Only gets subdivided for analysis in the solver, rather than getting subdivided in real space, so that you don't lose the actual geometry of what you modeled. So that's a big advantage over some of the other softwares that exist in the market. Now let's go ahead and turn back on the rest of the model. One of the other things that we have available in this particular model, if I turn on our support conditions and I just make our scaling a little bit bigger, is we have the ability to apply subsoil supports. And so this is the ability really to create an elastic foundation support for the use in the determination of a bearing capacity. So the user can modify the subgrade modulus in order to change that flexibility in the soil. And so if we want to go ahead and look at a particular result, we can go ahead into the 2D member contact stress result, and then choose a load combination or a class in this case, and then choose our value here. And I'm going to go ahead and run the contact stress, and so we'll just get generated contact stresses here. And so this is going through and doing all the contact stresses on all of the members here, and so you can see this based on our you can see it based on our finite elements. You know, we've got larger finite elements over here. I put some smaller ones over here, and so we can see in PSF, you know, where our bearing, you know, where our highest bearing pressures are, and you can compare this to your allowable bearing capacity to see if you've got any issues, right? And so this is a quick way to use that real soil condition to kind of really see how the structure is being supported. Now, what if you wanted to do something like a load takedown or something like that? Well, in this particular case, let me just go ahead and select, I'm going to select kind of a frame in the middle here. So I'm going to grab that frame, and then I'm going to choose a new activity, which is activity by selection. So we just want to see this particular set of elements. And with that, we can go ahead and look at, you know, the internal forces on the beam and maybe just show the axial forces in the current member. And so I just selected one particular member, and we've got the current forces in that. And so we can see here the axial forces where it's stepping, obviously, because we have the support for the chute here, and then we've got the support for the floor, and so we can see these different amounts. Now we can change the units, so we don't have to use pounds. We can use kips or whatever. We could always look at this in a table result, and that just opened on my other screen. So here's that table result. And this table result can be modified. You can see the information here. You can directly export this to Excel. You can really do whatever you want with this. You can send this into the engineering report. It's really completely up to you. Now within this steel frame, we can also do design, right? So there's obviously a bunch of other results here, and these are all code independent results, but we can also go ahead and look into the steel design. So if I choose steel and go into our checks here, we can go ahead and just run a check of these particular elements. So this is all these column elements I have selected here, and so we can see based on the drawing here, and let's change the way this is drawn so we can see this a little bit better. We can see the unity check on these particular elements. And so, you know, we've got a max unity check of 23% or 52% here. And so we can go ahead and look at this column and really see what's kind of going on. And so if I switch this to global, because I only want to see one, let's go ahead and look at what we have here. And so this is the actual steel check. This is step by step what's going on. So here's the size, the stress, the classification for flexure and compression, the unit or the internal forces, all the different elements. Now my units in this particular case for stress are set in meters and kilonewtons. I could easily go ahead into the units here and change my results. Let's see, what results am I in? Yeah, so I could just switch some of my results here so that we don't see results in that fashion. So it's really up to you. And so you can see then how we arrive at this 52% number. Zoom in a little bit here. So we can see how we've arrived at that. There's a little bit of torsion, and so that's taken into account. So all these different provisions from the steel code check are taken into account during this particular design. Now, one of the ways that this is taken into account is for steel, obviously, is using buckling, right? And so SCIA has a bunch of different ways to kind of go about looking at buckling, but one of the simplest is, and one of the ones that I just want to spend a little bit of time looking at, is what we call graphical buckling. And so graphical buckling is really exactly what it sounds like, but it is a methodology to graphically see exactly what's going on in a particular run of the structure. So in this case, we can see the element that we've selected. We can also see where it's braced for buckling about the strong and the weak axis, right? And we can see those different locations, obviously down here at the pier, the first level, the second level, and then let's call it the roof or the top level. And so within this, we could see this, but we could also just disable some of the buckling restraints to change our unbraced length. So it's very easy to do that as well. Now, this is great for a member-by-member buckling, but obviously you wouldn't want to do this for every member. That's why we have what we call buckling in relative lengths, where we can set basically a provision for a group of members. So in this case, we could set all these kind of columns to be completely buckled for strong and weak axis bending at all of their brace locations. And now SCIA will do a lot of this for you by default. So if I wouldn't have changed anything, it would have had default provisions based on what's actually framed into this, right? So the default in this case may have been that if there was nothing framed into the weak axis that, or the strong axis, excuse me, then it wouldn't have had a strong axis bracing. It would have known that automatically. But we can change that, manipulate that however you want. Now we also included in this, and let's go ahead and turn our rendering back on so we can see what we're doing here. Included in this is our concrete design, and so kind of in the back here you can see this this concrete wall. And so with that, we can go ahead and look at the concrete design. And so the concrete design is available in the concrete service. And so I think the best way to show this is just in this short little video that I have. And so it's just so we can kind of do this a little bit more efficiently. And so we can go into the member design, and in the member design we can choose what we want to look at. So we're going to look at required reinforcement. And so for this required reinforcement, we can also look at the level. Do we want the interior or exterior face in the positive or negative direction? Basically, that one direction is in the positive X direction. And so once we see that in the graphical interface, we could also go ahead and look at that in a table. And so in the table we can see, okay, interior and exterior, what kind of reinforcement do we need? What kind of shear reinforcement do we need? And so we can view different amounts of reinforcement in different directions. So now if we look at the opposite direction, we get a different amount of reinforcement. Now we can also look at maybe what type of user reinforcement we have in here. So I've already applied some reinforcement to this. So you see I've applied 0.62 square inches per foot. And so what that actually looks like is a reinforcement mesh that I've applied. And so if I go ahead and just quickly enable the reinforcement region, we can see here this is actual reinforcement that we applied. And so this is number 5s at 6 inches on center. That's how we get our 0.62 square inches per foot in both directions. And so we have applied that on this case on the upper face and the lower face, but we can go ahead and apply this reinforcement and then validate that this reinforcement works or not. And so in the member design again, we can go ahead and check. Then instead of looking at user reinforcement, we could go ahead and switch the user reinforcement to additional reinforcement and kind of see what we need to do. Okay, so the last thing I wanted to mention is that there's always the likelihood that a software doesn't do a type of check for you, right? It doesn't do something that you need it to do, it doesn't do something that you want it to do, or it doesn't do something the way you want it to do it. And so in that case, SCIA has something that we like to call open checks, or in the software it's called integrated design forms. And essentially what this is the ability to create your own checks and then integrate them directly into SCIA Engineer. And so in this case I have, maybe I wanted to, we don't do baseplate design directly in the software, but we do have a baseplate design for free download on our website. But in this case I've actually integrated this into the software. And so I could go ahead and assign that I want to do a baseplate design at that particular node, and I can assign the provisions of this particular baseplate design. And so just make this box bigger here. We can go ahead and see, how do I want, what I can set up my shear transfer and what my baseplate's like and what my welds are like and what my anchor bolts are like and what my reduction factors and support and design options. All this stuff can be set so that when I run my design, I get real results in the software. And in addition to that, I can also use this as a standalone. So this is that same design form, in this case, used as standalone, and we can see all of this information can be available in the software. So these outputs, if I look at like the detailed output that shows the checks step by step with everything filled out, this is all available in the software when you integrate a design form. And so you can create this allows you to really create anything you want and make checks that maybe you have in Excel or you've got in MathCAD or you're doing in TEDS or you're doing in InterCalc, you're doing by hand, really allows these to be integrated so that you don't have to create new, you don't have to export data from your finite element analysis software or your larger building model. You can include all of that in one place. And really the advantage of that is being able to coordinate that all when you're doing documentation. And so that's really the last part of this, is that SCIA has the ability to create what we call an engineering report. And so the engineering report really is a full-on robust reporting feature that exists right inside the software. And so this is a separate executable, and so what that means is that it works interactively back and forth with SCIA Engineer. And so if I make a change in the model, that change is then reflected in this engineering report. And so we can see we can put in model views or different different tables with information for cross sections or materials, or put different screenshots. When we save a screenshot, that screenshot is saved in the inbox, and so we can go ahead and look at a picture of contact stresses or 3D displacement on this particular tank or internal forces on this. We can look at all this different information. We can add in our steel code checks or our check of reinforcement. All this information can be put right in the model, or excuse me, right in the report. And you can see that if things are out of date, I'm not going to go ahead and regenerate the report right now, but if things are out of date, you'll be notified by this little exclamation point. It'll tell you that, hey, the information that's in the report is different from the information that's in the model. You need to regenerate that. And now one of the great features of the report is not only being able to build the report, but then once you build the report, being able to save it as a template. And so you can take anything you want, any amount of information, any amount of pictures or data, you can save it as a template. And then the next time that you do a project, instead of building the report from scratch, you just open the template, drop the template into the navigator. It will populate all of these items, and then you just refresh it with the information from that particular model. And so it's being able to leverage the work that you've already done to create a template for that particular type of project, so that you don't have to spend your time creating documentation over and over and over again. And so all of this can be used interactively with the software and the engineering report. You can also then export this directly to PDF, obviously to Bluebeam, which is another Nemecheck company, to do your markups and stuff like that. And so the engineering report is a really nice feature that allows you to not only to create good documentation at the end of a project when you need to give things to an owner or a municipality or something, but also during the project when you're looking to work interactively, when you're looking to send information to another engineer or send information to another trade, or even just look at different design iterations. Being able to lock results in the engineering report allows you to have multiple design iterations in the same model without having to remodel. And so we have all these functionalities for the engineering report, and it really allows you to kind of round out the workflow of creating and doing this kind of industrial type of structure. Now, finally, we have some really nice, the kind of final part of this project, right, is that, you build your model, you do your analysis, you do your design, you create your documentation. Well, then you need to obviously exchange data through interoperability with, downstream with maybe a fabricator, whether it's Tekla or now SDS2. We have interoperability with both, whether it's through IFC or direct links. And so both of these are opportunities to exchange data and really continue this kind of BIM workflow, even on a project where maybe there aren't even architects. And so one thing that I like to finish on really quickly before we open up the floor to questions is just some example projects. We do a user contest every 2 years, and users submit their projects. And so a few of these projects are from that user contest, and they're just examples of kind of industrial structures that have been completed in SCIA Engineer. So this here is just some grain silos. We've got a few different tank or grain companies that use SCIA in the United States. And so this is a really nice way to utilize SCIA, the automatic meshing, the plate structures, etc. A structure similar to the one that I was kind of creating, where we have this supporting structure for a piece of equipment or a tank or a hopper. And so obviously you can see this supporting steel structure being able to be now including this IFC data. So this is from IFC, being able to include this right in the SCIA model so that we can model around it. We can even get into pieces and parts, so doing something much smaller. So obviously this is maybe not small, but certainly not a building. This is obviously very large, but again, still not a building, but an application where we're modeling really down to how plates are interacting and wanting to see maybe, the ductile nature of a particular plate failure or something like that. All of that, again, is possible. And so like I mentioned, there's a few different free design forms that are out there. The column base plate design form as well as the HSS design tools, both are for free download. there's the links. If you're interested, if you missed the website, you can just go to our website or just search SCIA baseplate or SCIA HSS design tools, and that'll be the first website available to you. And you can download those for free and use them at your discretion. And so with that, I want to open up the floor to some questions. I know we've gotten a few in here, but if you see there's the chat window, or not, excuse me, not the chat window, but the questions window. You can go ahead and enter the question in there, and we'll take some time to answer a few. And so while you do that, let's see, there are a few questions. The first is a question relating to using truss properties for braces in SCIA Engineer. And so I'm not 100% sure exactly what you're asking, because you're referring also to STAD, but you can set an element to be a truss element. You could set elements to be truss cords and to have interaction, so maybe they would be axial only, so they're not going to take any bending or whatever. And so that is certainly possible. That's just an option to select. When you select an element in the properties, it would say, axial only. Obviously, as a nonlinear type, you can always set it to tension only or compression only, so on and so forth. And then there's some questions with interoperability with SmartPlant 3D. It's a question that we get pretty often, and so we don't have direct interoperability with SmartPlant 3D, but we do have interoperability with SmartPlant through both IFC and 3D DWG and DXF. And so that's really what when we see people doing those types of projects and using SmartPlant right now, that's typically the way that they're doing it, whether it's exporting an IFC file or using a series or a large 3D DXF or DWG to export the different portions of that type of structure. There is also a question, is there any way to subject the thermal loads for the equipment in existing power plants? So yes, so there are thermal load options in SCIA, both on 1D members and 2D members, and not only just along the length of a 1D or 2D member, but you can also change the thermal load that's applied as it goes kind of through the plate. So, if you said the thermal load on the inside of the plate was different than the outside of the plate, that's possible. As far as the equipment is concerned, the equipment is not going to be designed in the software. It's not a structural object, and so the software certainly is for the design of structural objects. You could probably model in using plates a piece of equipment or something like that, and then do an analysis of with those thermal loads on that piece of equipment. But typically, when people are utilizing equipment in the software, they're utilizing it as kind of a 3D representation so that they can create a supporting structure around it. There's some other questions about transfer, and so like I mentioned, the main transfer, whether it's main transfer with a variety of softwares, is using the IFC file format. There's also some direct transfers with Revit and Tekla and SDS2 and XML and step files to a variety of different softwares. There's a question about trials. We do trials of the software. You can just visit www.scia.net to download a free trial. You can just, it's a free 30-day trial. It's the full version of the software. There's no limitations except for a watermark in the engineering report. And so you have full flexibility to really do whatever you want in that case. Let's see another question. So there's a question about cost, because the software seems to have a lot of different functions, and that's true. It does have a lot of flexibility and a lot that it can do. The nice thing about SCIA is that it's also scalable. So you don't have to buy the package. Although it's one package, the package can be smaller or bigger. So we sell typically in 3 versions in the United States, what we call the Starter, the Fundamentals, and the Professional Edition. And those obviously have different prices, with the Starter Edition starting somewhere right around $3,500. And so you can get a lot of work done. You can do a lot of analysis, a lot of all the modeling, all the loading, all the analysis, nonlinear analysis, and design of steel and 1D concrete members in that Starter Edition. And so really the the larger editions add more advanced analysis, more advanced loading, and more design codes. And so it really depends on what you want, but we could certainly build you a very custom edition that fits your needs and also your price point. Okay, well, if there are any other questions, please go ahead and enter them into the question field now. But I think that at this point, we can go ahead and wrap up. So thank you very much for the participation, and we hope you enjoyed your time. Post the webinar, we'll process and send out the certificates for the webinar. So you can probably expect those by about Monday, just after everything gets filtered into the system and through it. The webinar will also be uploaded to YouTube, and that should happen either later today or again probably tomorrow. And then if you have any questions, my email address is listed here on the last slide. Please feel free to email me if you're interested in learning more or setting up a demonstration for your office. We're more than happy to do that. So with that said, I thank you very much for your time and participation. I hope you have a great rest of your day, and we look forward to hearing from you and working with you with your company and SCIA Engineer. Thanks very much. Bye-bye.